Okay, in today's lecture, we're going to introduce the notion of two fundamental types of functions that we haven't encountered before, at least in the calculus course. And those are the logarithmic and the exponential functions. This lecture and the next lecture are going to focus primarily on the logarithmic functions, or the natural logarithmic function. But we are going to also mention about the exponential function because they are intimately related, as we will see, not this lecture, not next lecture, but probably the lecture after that. So we'll begin by first recalling that there is a special condition on the power rule for antidifferentiation. So just first recall that the antiderivative of x to the power n dx, there was a formula for this, right? It was just x to the power n plus 1 all over n plus 1 plus c, provided that n was not equal to -1. Okay. Now that specification that n was not equal to -1 was important, right? And in particular, we don't know, well, currently we don't know how to find the antiderivative of 1 over n, right? If n is equal to -1, so how should we consider maybe the antiderivative of 1 over x dx, right? Again, if you take n to be equal, if n is equal to -1, then it's 1 over x, and the power rule that we have doesn't apply in this case. So how should we think about this? Well, we're searching for the antiderivative, right? So we have some function that we're seeking whose derivative is equal to 1 over x, which means that we can sort of get a picture of what this antiderivative looks like, right? Because if we want the derivative to be that, right, then this value gives you the slope of the tangent line to the curve at any of these points, provided x is not equal to 0. So let's kind of see if we can figure out what that looks like. It's like 1, 2, 3. Okay. And we know that dy dx, where the y is the antiderivative that we don't know, right? We know that that derivative is equal to 1 over x everywhere, right? So if we think of this as a differential equation, all the solutions to this would kind of tell us what the antiderivative is, right? Or what the solution to this is. So when x is equal to 1, okay, the slope of this function is going to be 1, right? And I'll just tell you that if we're not raising up anything, we can kind of think of this as like slope 1. And again, we're going to define exactly what this is in a moment. I just want to kind of talk about what the derivative of that thing we don't know is doing. Okay, at x is equal to 2, the slope is 1/2, right? When x is equal to 1/2, the slope is 2, so it's steeper. When x is equal to 3, it's even steeper, right? So we can kind of get a sense of what the original function is looking like just by looking at the derivative. And in many of our previous lectures, we've learned how the derivative can tell us the shape of what's happening for the original function. So we'll come back to this maybe later in the lecture. Now I'm going to go ahead and define what we're actually looking at here. So that's the definition. So the natural logarithmic function is defined, and there's actually several ways to do this, but this is how we're going to do it using calculus. The natural logarithmic function is defined as ln of x equals to the integral from 1 to x of 1 over t dt. And this is for t greater than 0. So this is how we're going to define our function natural log of x. So what does this look like? Well, we can interpret this as the area under a curve, right? So that's our curve, 1 over t. Okay. So 1 over t looks something like this. Now this curve is not natural log of x. This is 1 over t, okay, for t greater than 0. This function is equal to the definite integral from 1 to x for a given x. So if this is like 1 right there, and x would be like maybe like right here, then this value is equal to this area. Okay, so this right here would be the value of ln of x, natural log of x. And we see that if x is greater than 1, then this is going to be a positive area, right? Some positive number. So we can go ahead and like observe two things right off the bat here. If x is equal to 1, then we have that, well, I'll just write it out. Natural log of 1 is equal to 0, right? The integral from 1 to 1 of any function is going to be 0. We learned that in the previous lecture. If x is greater than 1, then the natural log of x is going to be positive. And it's just this area, right? But we learned that if we have our limits of integration where the lower limit is less than the upper limit, so if like x goes over here, I'll say like x naught maybe, then if x naught is less than 1, that area is going to have a negative in front of the integral, the definite integral. So we can also observe that if x is less than 1, then the natural log of x is less than 0. Okay. What's more is we can see that this integral is going to be defined for all x greater than 0. So the domain of this function is going to be 0 to infinity. Okay. And by the way, when I was making this plot over here, I knew ahead of time that when x is equal to 1, the natural log is equal to 0. So that's natural log at 1, and the slope is 1 over x. So the slope of the line touching the curve right there is going to be 1. And we connect all these points, we get that this is ln x. And then the solutions to this is ln x plus c for any constant c. So what we really get is a huge family of antiderivatives of that function. But the most simple one, c is equal to 0, is this one right here. Slope of the tangent line there is 1, slope of the tangent line there is 1/2, 1/3, slope of the tangent line here is 2, 3, so forth and so on. Okay. Okay, so as you might recall from maybe a college algebra or pre-calc class, there are properties that the natural logarithm will satisfy. And I'm just going to recall those here at the statement of this theorem. So if A and B are positive reals, and say n, yeah, I'll use n, and n is rational, then we have several properties. So we've already discussed this one. The natural log of 1 is equal to 0. 2, the natural log of A times B is equal to the natural log of A plus the natural log of B. 3, the natural log of A divided by B is equal to the difference of the natural logs. And then finally, or 4, I think that's how I've listed it. No, it doesn't really matter. So ln of a to the power n, you can take down that rational, write it as follows. Okay. Now, because we need to cover quite a bit in this course, and kind of, this is typically a Cal 2 topic that we spend quite a bit of time on, I'm just going to refer or maybe post a YouTube video for you to review these properties. Because they're going to be really important when we look to integrate and differentiate logarithmic functions. So these are important, all of them. And this one is quite useful. I like this one the most, I think. Okay. Okay, so now let's go ahead and make note of one special number for this function here. So this is Euler's E. So the number E, and this is one way to define it, is the number satisfying this equation. Right, so among all the choices of x here, one of these choices, so we have negative values for the natural log, if x is on this side, natural log is equal to 0 right there, and the natural log becomes positive as we have x increase past 1. Among all of those values, there is some number for which, oh, I almost, there. There is some number, some choice of x past 1, where the area under this curve is going to be equal to 1, and that's what we define the number E as. Okay. Okay, so these are the basic definitions that we're going to be working with. And now we can write down a theorem and then do a bunch of examples. So let me pause the video and clean the board up. Okay, so now that we've given the definition of the natural log, the number E, we know the basic properties of the natural log. Domain is 0 to infinity. It's increasing because it's increasing in concave down. Actually, if you follow the slopes of the tangent lines. So now we have that information out of the way. We can now state the main theorem that we're going to use to take derivatives of natural logarithmic functions. So if u is a differentiable function of x, then we have, well, 1 is really a special case of 2, but I'll state it anyhow. The derivative with respect to x of the natural log of x is equal to 1 over x. Okay, that's just recalling the definition that we wrote down. If we take the derivative of the integral, we get the inside, and that's where that comes from. In a similar fashion, the derivative with respect to x of natural log of u, where u is a function of x, is simply, well, we apply the chain rule. The derivative of the outside, which is 1 over u, times the derivative of the inside, which is u prime, which is that, provided u is greater than 0. And a special and useful observation, I suppose, is that if you have the natural log of the absolute value of u, and you take the derivative of that with respect to x as well, then you also get u prime over u, provided u is non-zero. Okay. So if u is greater than 0, you don't have to worry about the absolute value, but you can include the absolute value provided u is never 0. Okay, so let's look at some examples. We'll start simple, and then we will build our way up to something that's more complicated. So example maybe A. Let's look at, I don't know, let's say d dx of natural log of 2x. Okay, so here, if you want to write out every step, you can say maybe like, so we say let u equals to 2x, and that is a differentiable function of x. So then this becomes d dx natural log of u, which is equal to, well, the derivative of the outside, which is 1 over u, times the derivative of the inside, which is u prime. And u prime is just 2, right? And then u is 2x, we get 2 over 2x, which is equal to 1 over x. And again, provided x is greater than 0. Okay. So let's look at another one. Let's look at the derivative of the natural log of, say, 2x squared plus 1, something like that, right? So again, we can write this as ln of u. So if we say let u is equal to 2x squared plus 1, and then u prime is equal to 4x. So then I'm writing out a few more steps than I would typically do, just so you can see how to apply the rules. Like that. And then we have that this is that. Not too bad, right? Okay, so maybe let's look at another one. So let's look at the derivative with respect to x of natural log of x all cubed. So here we need to apply the chain rule first, right? We have something cubed and then something else inside, right? So this will be the derivative of the outside, which is 3 times natural log of x all squared times the derivative of the inside. and this becomes 3 natural log of x all squared all over x, because the derivative of natural log of x is just 1 over x. Okay. So again, this, and you're going to end up using this rule so much that you'll memorize it. Right now it might seem a little foreign, but just you'll get the hang of it. Okay, so I'm just going to leave this rule up here so we can reference it. And then finally, let's look at the example D. We differentiate f of x equals to x times x squared plus 1 all squared divided by root, say x, what did I have written here? 2x cubed minus 1. Make sure you can see that. Okay. Yeah. So here, what can we do? Oh, wait a minute. We could do that, but let me rewrite this real fast. There's a natural log in front of that. So this is one of these examples of a topic in Cal 2 where it just gets really messy. And you need to have a lot of room, which is not going to be fun for me because I only have this much room here. So let's look at this. So here for this problem, we're going to first rewrite f of x using the properties of logarithms or natural logarithms. So first I'm going to note that I have a difference here, which I can write as, I have a ratio, natural log evaluated as a ratio, which I can then expand as the natural log of the difference of those things. So here's the numerator minus natural log of the denominator. Okay. Now also, I see I have a product here. So the natural log of a product becomes the sum of the natural logs. So it's going to be equal to natural log of x plus natural log of x squared plus 1 all squared minus natural log. And I know that this is a 1/2, so I can rewrite that as the power. Like that. So then I can apply that exponent rule for natural logs and bring the exponents in front as a multiplying by a constant. Okay, so at this point, there's no further logarithmic rules I can use. Right, so this is what f of x really looks like. And now I just need to differentiate this function here with respect to x. Okay. So then let's see if we can do this quickly. So f prime x is equal to, so the derivative of this is 1 over x. The derivative of this is 2 times 2x over x squared plus 1. Okay. Right, it's the derivative of the inside divided by the inside. That's basically how you take derivatives of natural logs. And then here we have minus 1/2 times. So we know in the denominator we're going to have 2x cubed minus 1. And then in the numerator we're going to have 6x. So then all together, we have 1 over x plus 4x all over x squared plus 1 minus 3x over 2x cubed minus 1.
Would that last one be x squared on the numerator?
Would be. It would be. Thank you for catching that. Okay. So again, you're going to encounter from here on out expressions that might look a little messy, and you're going to have to, well, in this case, if you have natural log of something jumbled up like that, apply your natural logarithmic rules to break it into smaller little pieces, and then differentiate each small piece. All right, so again, let's look at another example. Suppose we have example E maybe. So maybe like find y prime when y is equal to x root x squared plus 1 for x greater than 0. Okay, so we could use a combination of the product and chain rule to find y prime here, but we can also do this by what's called logarithmic differentiation. This is defined for x greater than 0. So because of x being greater than 0, that's greater than 0, which means that we can take the logarithm on both sides. After doing that, because we know how to find the derivatives of natural logarithms, we can use implicit differentiation to find y prime. So this would be considered a technique of logarithmic differentiation. But very carefully, though, you need to observe that's non-negative. The logarithmic function is, the natural log is not defined for negative inputs. So when we take natural log on both sides, you have to be very careful of that. So we take natural log of y is equal to natural log of x times root x squared plus 1. Which means that natural log of y is equal to natural log of x plus 1/2 natural log of x squared plus 1. And you should verify that that's the case. Right on the right-hand side, we have that times that, so I can break that into a sum of natural log of the first plus natural log of the second. There is an exponent of power 1/2 right here. I can bring that in front and multiply as a constant by that rule for natural logarithms. And now once we have this, we can differentiate with respect to x on both sides. Okay, and again, we're using implicit differentiation here, so we're treating y as a function of x. So basically, your y is like your u, in a sense, from this theorem. So here, derivative of natural log of y, well, y is a function of x, it's just going to be y prime over y. Derivative of that is just 1 over x plus 1/2 times, so the derivative here is 2x over x squared plus 1. Again, it becomes really easy actually when you're looking at natural logs. You take the derivatives, it's just place that in the denominator, put the derivative in the numerator. So this looks like y prime is equal to y times 1 over x plus x over x squared plus 1. Okay. And then we're pretty much done because we know what y is, right? Y is that. And again, we're trying to find y prime, the derivative of y. So this is going to be x root x squared plus 1 times x, oh no, sorry, 1 over x plus x over x squared plus 1, and whatever that evaluates to, right? If you did distribute that in, you'll have root x squared plus 1 plus x squared times root x squared plus 1 over that. So I'm not going to waste word space on that. Just know that you would distribute in and kind of simplify it out. Okay. So this was a solution by logarithmic differentiation or implicit differentiation. It's just a technique. Okay. So that was a quick run through of taking derivatives of natural logarithms, and I think this is a good time to stop the video. But first, maybe I'll write up homework problems for the students in this section. 21 through 25, 31 through 35, 43 through 61, 70, 81, and 83. And these are suggested homework problems. These are not to turn in, but I highly suggest that you do them and check the answers in the back of the textbook. Okay, so that will be the end of this recording.